Okay, in this section we're going to be looking at this particular orthogonal set. The last example in the previous section, we looked at a set 1, cosine x, cosine 2x, and so on, and we were able to show that it is orthogonal. You can do something really similar with this pi over p on the interval from minus p to p, where p is a particular constant, to show that this is still orthogonal, and it turns out it's even orthogonal when you add in infinitely many signs that look the same. So we have 1 infinitely many cosines, pi x over p, 2 pi x over p, 3 pi x over p, and so on, sine pi x over p, 2 pi x over p, and so on. What we'd like to do now is try and find a series, which is constants times each one of these all added up. And so I'm just going to jump straight to what that's going to look like. We're going to have a constant times 1. We're going to have a constant times each cosine, which are all in the format n pi x over p for some n, and constant times some sine, which are each of the format n pi x over p for some n. And so we're taking a sum of all the n's because we're adding up all the cosines and all the sines. So this looks already way weirder than any series we've seen before, because all the series we've seen before have been power series that they had just a power of x. Now we have cosines and sines. Also, we don't just have a single series, we have two different series. We have cosines, we also have sines, which means we have two different sets of constants. We don't just have like a cn, x to the n, we have an's going with cosines and bn's going with sines. So not just infinitely many constants, we have infinitely many constants, infinitely many more, and then one left over which is associated with 1. And you'll notice instead of being a0 times 1, I've actually done a0 divided by 2 times 1. And the reason for that is so that a0 and an have kind of the same formula. So this 2 is going to be important in that it's going to make our lives easier down the road. Okay, so the next thing we have to figure out is how do we solve for these constants? What are these constants going to be? So if I told you that the function you're interested in is x squared, so if f of x is equal to x squared, and we want to find a series that's multiples of cosine plus multiples of sine that ends up being equal to x squared, we would have to solve for all these constants. And the magic of inner products says that that's not actually going to be terrible. And the reason being that if you do an inner product of both sides with, say, 1, then we end up with something ridiculous, but these are orthogonal functions. The inner product of them should be 0. These are orthogonal functions. The inner product of them should be 0. And so that means a whole bunch of things are going to turn into zeros. We're going to end up having a not too terrible time solving this equation for a0 because our inner product is actually an integral. And so I'm going to jump straight to what are the formulas going to be. The formulas are going to be a0 is an integral 1 over p, definite integral from minus p to p of the function f of x. An looks similar, only it has a cosine in there. Bn looks similar, only it's got a sine. And so then I said originally that our whole idea here, the reason we have a0 over 2 is so that a0 and an have kind of the same formula. Actually, all three of them have same formula. Every one of them, the definite integral is an inner product on our domain of f of x times the corresponding function. So f of x times 1, f of x times cosine, f of x times sine. So each of these is an inner product, and then all we're doing is dividing by p each time. If you wanted to, you could look at the proof in the book of why exactly these are the formulas. They're actually called Euler formulas. We don't really care about them. We're not going to try and memorize these formulas or even this formula. We just need to be able to use it when we need to. And that's going to come up in the next couple of sections, times where we need a Fourier series. Okay, I have one more thing I still need to talk about in this video, and I need some notation to be able to do that. So I'm going to define f of x plus to be the limit of f of x from the right, and f of x minus to be the limit of f of x from the left. So So number slightly smaller than x versus number slightly bigger than x. And the reason we need this is it turns out that the function f of x and the answer we get from the Fourier series aren't necessarily going to be the same. And the problem is that the series may or may not converge. So what's going to happen is the Fourier series, it turns out, should converge, but it's going to converge to f of x if f is continuous, and it's going to converge to something different if f is not continuous. So if f is not continuous, it's actually going to converge to this weird thing, f of x plus f of x minus, which is your limit from the right plus your limit from the left, and then we take an average of those two numbers. So this is a little complicated. I'm not going to try and explain this in this video. In a future video, I'm going to show you the graph and what the significance of this is.